Today we're in Chapter 2, which probably doesn't mean a lot to you because you're probably not actually looking at a book, right? But there is an ebook in your homework that you can read, right? And it's not bad. It's there anyway. So today we're supposed to talk about graphs of equations, graphs of functions, like what is a function, how you evaluate a function. So these are sort of basic things. And these topics are, very, very important, especially if you're going on. I think, how many people, this is not your last math class here? This is your last math class here? Not your last math class here. 1, 2, 3. I think everyone here pretty much this should not be your last math class. Like, you probably have to take what 113 after this, right? The pre-calculus algebra, or maybe you go a different direction. What's the course you're going to take? I don't think everybody goes to pre-calculus. Other people go to, what is it? Is there a discrete math class that you have to take for like computer science? I'm actually curious. I don't have photo recall of our courses yet here. I'm still new. In any event, this is not the end of the road, and wherever you go past here, almost certainly you will face the problem of analyzing what a function is. All right. So today we're going to talk about graphs and functions. So graphs of equations and functions. So this should span the material from section 2.1 to 2.3 in the text, all right? So we should just start out with the basics, right? Like, what's our context here? Well, the basic thing is, if you have a pair, A comma B, right, corresponds to a point, right, in the xy plane. All right. Now, the xy plane, I don't think your book probably does this. It may or may not. I don't remember off the top of my head, but mathematicians like to call this thing R2. R2 is the xy plane. It's also R cross R, all right? It's the Cartesian product of the real numbers and the real numbers. So R cross R is, what is this? Well, R2, it's x comma y, such that x is a real number and y is a real number. Now, I know I'm using some kind of funny symbols. So what's this thing mean? I'll just remind you, this was element of, right? So let's look at an example with some numbers. Let's plot A, which is, let's say, 2 comma 4, B, which is minus 3 comma 5, C, which is, let's say, minus 4 minus 10, and D, which is, let's say, 3 comma minus 2. Let's plot these 4 points in the xy plane. All right. So I'll do the best I can, without having graph paper up here, but just to sort of set the scale here. Here's my x-axis. Here's my y-axis. I'm going to draw like a dotted box that sketches, say, minus 10 to plus 10, right? So just to give us kind of a reference frame here. Let's say that this is it goes to plus or minus 10. So like, excuse me, this is minus 10, right? This is 10. This is 10. And this is minus 10 in terms of x and y coordinates, right? So where does A? Where does A fit in this picture? How do we get to A? Yeah, A is at 2, 4. You say it's in quadrant 1, 2, 4. That means we go do what? Go 2 to the right. And you said 4 up, right? 2 to the right and 4 up because they're both positive. So, so that's something like, let me see here. So this would be 2, 4. I don't know. It's hard to space these things out, right? You know. I guess I can do the halfway point. That's 5, right? I'll try to judge things by my 5 marks here. So 2, let's see, goes 2 over and 4 up. So that's just about here-ish, right? That's my A, point A, right? How about B? What's that mean? B is minus 3, 5, right? So go 3 to the what? Left, right? And we go 5 up. So we go 3 to the left, we go 5 up. That's about here, right? How about C? Let's put that into words. What does it mean to have the point minus 4, minus 10? That means we go 4 to the what? Left, and go 10 down, right? Minus is down. So we go 4 to the left, and 10, so it's like here-ish, right? All right, and finally D, we've got 3 minus 2. How's that work? Sorry, I was coughing needlessly. So you said go 3 what? 3 right, and down 2. So that would put us kind of like about here-ish, right? All right, so just to reiterate, this is how we plot points. The x component tells you how you go to the left or the right. The y component tells you how you go up and down, right? There are 4 quadrants. What are the 4 quadrants? How do we number them? This is quadrant 1. This is quadrant 2. This is quadrant 3. And this is quadrant 4. I'm using, what are these kind of things called? Roman numerals, right. It's one of the shortcomings of my children's math curriculum. We use, we homeschool, and my kids, they use this thing called Singapore math. Singapore math, for whatever reason, does not have Roman numerals. So it puts them at a disadvantage for certain standardized tests, because Roman numerals are something that's kind of like a standard part of our education, right? Like, you need to know Roman numerals if you want to know when movies were made, right? At the end of every movie scroll, there's got that like MCM, blah, 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 you know. Good luck figuring that out. Anyway, so can you guys tell me, let's put it into words. Quadrant 1 has both x and y positive. Quadrant 2 has x negative, y positive. Quadrant 3 has both x and y negative. And quadrant 4 has x positive but y negative, right? So this is important if you're solving an equation and you're trying to decide between a couple different choices, right? If you know that the answer has to be in one of those quadrants, the signs, like the plus and minusness, if you will, of x and y is very instructive as to how we solve equations. You'll see that as we go on. So there's an example. Okay, so that's the xy plane. Are we good? Okay. So what is a graph of an equation? Right? So if, let's say, f of x comma y equals to, like a constant, is an equation, right? Then the graph, let me call this equation. I'm gonna need to give it a name. What do you guys want to call it? Let's name it Bob. There we go. The graph of Bob, what is that? It's x and y such that what? Such that the equation holds true, right? So in this case, such that f of x comma y equals to that constant, right? What does the graph of an equation look like? I guess I should number this. This was example 1 for today. So let's look at some examples. Well, how about this? If I had x equals to 3, that's an equation. What's the graph of x equals to 3 look like? Let's see here. So I heard 3 comma 0. Here's x, here's y. 3 comma 0. Suppose it's there, all right? I agree with that. Now that's part of the graph. Yep. Oh, you weren't raising your hand. She was indicating. Give me a sign for the graph. I like that. I mean, that we can't always do that, right? Like here. How about this one? Go. No sign? You need more elbows, is the problem. I'll come back to this one in a second here. I'm kind of getting ahead of the story, but this one here is a vertical line, right? Every point of the form 3 comma y solves x equals to 3, right? It doesn't matter what y is, everything on that vertical line solves the equation x equals to 3. Let me put it in other words. There is no restriction on y here. No restriction on y means all y are allowed. Right? My silly second example, my silly third example rather, really was just constructed so that there's no really good reason for this. This would not have happened if it wasn't for, what was your name? What? Oh, Layla. Giving me the sign motion there. So this one, I'm trying to remember. I don't know if we actually get around to graphing these this semester or not, but this one has what are called x-intercepts 1, 2, and 3. And it has a y-intercept of -6 for what it's worth. And it looks something like this. Now, I'm not saying that, I mean, you may or may not know how to graph that already, yeah? So this has, quote unquote, x-intercepts of 1, 0, 2, 0, 3, 0, right? And it has a y-intercept at 0, -6. These things are true about this graph. The red line is the graph. Let me make the other one red as well, just to kind of be, I'll try to make all my graphs red here for the immediate future here. Can you guys tell me what this is called? Graph of a what? It's a what? you said it's graph? You can't go wrong there, that's true. It's the graph of an equation, that's also true. Technically speaking, this is the graph of a function, which we'll talk more systematically about as we go on today. I can tell that because it passes the vertical line test. I'll try to explain more about that as we go on here, but this is a cubic, the graph of a cubic polynomial. This is a cubic graph. Cubic. I can't, my point was just to give you a stupid example that you couldn't bend your arm like. I think I succeeded that much, right? Can you guys bend your arm like that? I don't know, maybe, if I had more double jointed wrists, perhaps, I don't know, but okay, let me stop being stupid. Well, that's not likely to happen anytime soon. Let me give you more examples. Example 4. How about if we had y equals to minus 2? What's that graph look like? So what is the condition on x here? Yeah, that's right. There's no restriction, right? So all x work, all of them. So this is a horizontal line, right? So it has, here's this particular point in it. It has 0, minus 2, right? But it also has any point x comma minus 2 solves y equals to minus 2, right? This is a what? A horizontal line, right? A vertical line. Horizontal line. Comment. Generally, the solution set of ax plus by equals to c is a line. Right? So we've looked at some special lines, vertical line, horizontal line, right? But there are many others that are not vertical or horizontal, right? There's something else. So let's see here. Could we graph 3x plus 2y equals to, I don't know, 5? How would we do this? Well, if you had a graphing calculator, you might be able to figure out the function of your graphing calculator that graphs an equation. That may well be an option for you. If it's not in class, right, if it's something you can do out of class on a computer, certainly there are good websites for this, right? Like, I personally strongly recommend something called www.desmos.com. This is a very, very good math website. There's like a graphing calculator. It's free. You can share graphs with other people with or without editing privileges. So like if you're graphing something, you want to share it with a friend, you can send them a link to what you graphed. You can do other things like add a slider to equations, so you can modify the graph according to a parameter. Like you could, we'll look at I'll get Desmos out sometime and show you the many quirks and features of it. It's extremely useful, but we don't need all that here, right? If you believe my comment, this is a line. What did you guys learn in math at some point? How many points do you need to fix a line? 2, right? 2 points. Fix a line. Determine a line, right? So how are you going to find 2 points which solve that equation? How do you find a point that solves an equation? Get rid of a variable. How do you do that? Divide by one of them. Well, That is usually what we do. That's true. But before when we've divided by one of them to isolate the other, we've had an equation just involving one variable, right? If you think back to like earlier lecture, we did just an x or just, what's that? X-intercept. That's a good choice. We could look for x-intercepts and y-intercepts. Those would be 2 points that would determine the line. So that's a particular choice. Totally legitimate choice, right? But more generally, you could just guess whatever you want. If you think about a line, right? Unless it's a weird one like a horizontal or a vertical, right? If the line is not horizontal or vertical, what does it do? It goes on and on and on this way, or it goes on and on and on that way, right? So in either case, it hits all x values and it hits all y values. So it don't matter what you choose for x and y, there's going to be a corresponding other one that matches that in the equation. Like, now I like your x-intercept, y-intercept. That's super helpful. So how about x-intercept? How do we get that one? That is slightly counterintuitively, that is where y equals to 0, right? So in our equation, what do we get? Plug it in. 3x plus 2 times 0 equals to 5. So therefore what? What point do we get? We get x equal to minus 5/3, right? So that gives us the point minus 5/3, comma 0. That's our x-intercept. How are we going to find the y-intercept? Slightly counterintuitive, but this is how you do it. You look for where x is equal to 0, right? X is equal to 0 at the y-intercept. So we plug in x equal to 0. We get 3 times 0 plus 2 times y equals to 5, which tells me that y is equal to, how did I get minus 5/3? Yeah, you're about to ask that? That would have been a good question to ask because there's no minus there. What's wrong with me, right? Change that minus to a plus. All right. So 5/2 is where the y-intercept is, which tells me that the point 0, comma 5/2 is on the graph, right? Now, for the purpose of graphing, I think it's helpful to think about decimal numbers rather than fractions, right? Because we don't, I mean, if I ask you what 5/3 is, you may or may not know, right? But if I tell you it's about 1.67, we immediately go, oh, 1.67, okay, I know what that is, right? So this is roughly 1.670, and of course this one is what, 0, what's 5/2? 5/2 is 2.5, right? So with those decimal numbers, it's easy enough to kind of set a good scale here. So let's see here, 1.67 in the x, right? Let's say that's there, and 2.5, so it should be a little bit further up, right? In the y-intercept, like here. So there's my x-intercept, there's my y-intercept, and then how do we draw the line? You remember, we all like to do this. Connect the dots, right? So just and there you go. That's the graph of this equation, which of course is a line. All right? Any questions? So we'll talk pretty much the entire next class. We talk about how to find the equation of a line. So we'll come back to that next class. But just throwing it out there, this is generically speaking what a line looks like. It's something like ax plus by equals to c. That's going to be a line, right? This general format allows for all the different cases, horizontal, vertical, whatever. So any questions? There's a general principle at play here, which is to find an intercept. What have we done? we've looked where two equations are true, right? Think about this. The x-intercept is where what? It's where y is equal to 0, right? It's where y is equal to 0, and what else? And where this equation holds, right? So to find intercepts, when you have two graphs, what we're going to do is assume they're both true. And if both of the equations are true, that gives you the point of interception, right? So that's just this is a general principle. We're seeing kind of a low tech application of that, but here that's what that looks like. All right, so I've shown you some graphs here. Let me show you another. See here, example 6. If we have x minus h quantity squared plus y minus k quantity squared equals to r squared, this gives a circle centered at h comma k with radius r. All right. So let me put some numbers in here. If I had like x plus 2 squared plus y minus 3 squared equals to, oh, I don't know, 2. You could, if you see an equation like that, and you know this this result, that things of that form are a circle, then what? You could identify that this is a circle, right? So what if you believe my essentially theorem up here? What's the radius of this? Where's the center? The center is, let's see, if I got plus 2 and I have to match that pattern, I need what? I need minus a minus 2, right? So the center would be at minus 2, comma 3. What's the radius? If r squared is equal to 2, what's r? R is equal to plus or minus the square root of 2, right? But this is a radius, right? So we think about negative radius? No, right? So just throw out the negative solution. So we thus r is the square root of 2. All right. Now square root of 2 is about 1.4, something like that. 1.4-ish, right? So if I want to plot this thing, here we go. The center is at minus 2 comma 3, so it's about right here, right? And the radius is 1.4, so it's going to come down to about right here, and over about right here. So there you go. That the graph of this equation right here is this red circle. Okay? Any questions? I think we actually come back to the problem of finding circle equations later in the course. I'm just throwing it out here as an example at the moment. As always, what you're responsible for on the next test is largely governed more by homework. If I cover something in lecture that's not in the homework, that would kind of be like a bonus kind of question on the test. In other words, you could still make an A on the test without getting that problem right. Example one last example here for this general arc of the discussion. Example 7. Let's consider 3x cubed plus 2xy minus y to the 5th power plus 1 over x equals to 0. All right, there you go. That's an equation, obviously, right? It's an expression involving x and y with inequality. You could search the set of x and y which solve this equation, right? I can tell you some things about it. It doesn't include 0, right? 0 is not in the graph. X equal to 0, rather. It's not in the graph, right? Because 1 over x would be not defined there. But I'm not going to try to graph that like without some kind of software, all right? But I can ask you a specific question, like, is 1 comma 2 in the graph of the above equation? And so how would you decide? So the very heavy-handed and silly way to solve this is to get out a graphing calculator, to graph it, and then go look for the point 1 comma 2 and see if it's in the graph, right? I don't advise this course of action. There's a much easier path. What do? What's the definition? The definition is the point is in the graph if it is a point which, when you plug it into the equation, it solves it, right? So plug it in. Does it work? I don't know. So we do 3 times 1 cubed, right? Plus 2 times 1 times 2. So this is the recipe, right? We had to follow the recipe. Minus y to the 5th, which is what? 2 to the 5th? Plus 1 over x. So what is that? It's 3 plus 4 minus 32 plus 1, right? Which looks like 8 minus 32, so that's 24, minus 24. Now, is minus 24 equal to 0? Nah. Not equal to 0, right? So this point is not on the graph. Can you guys give me a related equation which would have the point 1 comma 2 on the graph? Now that we know plugging 1, 2 produces minus 24, right? I can tell you this, 3x cubed plus 2xy minus y to the 5th plus 1 over x equals to minus 24 does have 1, 2 in its graph, right? Because we plug in that point, we get minus 24. It's a relatively simple task to decide whether or not a given point is in the graph of a given equation, right? You just plug it in. Does it work? It works. If it works, it works. If it doesn't, it doesn't. All right? So that brings us to our next big topic. All right? Function. So f from A to B is a function with domain of f, which we also call this equal a, the range of f, I'm just going to assume is b, right? So you could draw different pictures to kind of like get this idea sort of schematically. There's this set A. These are A and B are sets, all right? So you have A, you got B over here, right? And what is F? F is something that transports from one set to the other, right? What happens, our notation, is we take X in the domain, right? Here's X. And what happens? You go under F, you map over here to f of x, right? X maps to f of x. Okay. Now, this f of x has to be a single value in B, all right? Now, for the most part in here, we're just going to let A and B be sets of real numbers. Like most often than not, A and B are like intervals or just sets of real numbers, okay? But you can define functions more abstractly if you want. I'll try not to do that in here. There are a few ways to define a function. There's three sort of common ways people talk about it in this class, in this sort of course. The one is just with a picture. All right, so picture is kind of hard to, a line diagram sometimes they're called. So there's a pictorial. Let me show you that. Pictorial. So maybe let's let A be 1, 2, 3, and we'll also let B be the same set. Okay. Well, let's let B be 4, 5, 6. All right. So you can draw a picture like this. Here's 1, here's 2, here's 3, and over here I can put 4, 5, and 6, right? Let me draw a couple of these pictures, all right? I'm going to give you one that's a function. I'm going to give you one that's not, all right? So these kind of diagrams. So let's see here. 1 goes to 4. 2 goes to 6. And 3 goes to 5. All right? So let me point out, this means that f of 1, so this is a picture of f. So what I'm saying is that f of 1 is equal to 4, f of 2 is equal to 5, f of 3 is equal to, oh, I can't do math. F of 2 equals to what? I didn't say 5, I said? 6 in my picture, didn't I? F of 3 is equal to 5. There we go. Now this is an example of a function because it's single valued. Each input gives you just one output. All right? Over here, let's say 1 does like this, 2 does like that, and 3 does like that. So I have, let's call this one G. So I have G of 2 equals to 5, G of 3 equals to 6. But what about G of 1? See 1 I have pictured here. G of 1 is equal to 4 and 5, right? This is forbidden. Function must be single valued, so we can't have two outputs from one input like this. So this right here says, oops, G not a function. Okay? So there's a few homework problems like this. I think this is useful, just as a starting point. What's A called here? A is the, for F, A is the domain, and B is the what? The range, right? For this one. Now this example, which I probably should number, example, where am I? 6, 7, example 8. There's no formula, right? There's no formula. There's just a picture, a guide, right? Uh-oh. Did I never? I'm trying to remember, did I? I'm not sure if I ever actually panned over here when we did the circle thing. I feel like I may have just been, well, 4040 is the timestamp. It'll be okay. I'll go back over here. All right. Now, do you guys remember functions from previous classes at all? Maybe? Do you remember this? I mean, I don't, a little bit, right? But this is not most of what we do, right? What do we usually do? How about this? You're given a formula, right? For f of x, right? So let's see here, some examples. This defines the function by rule of greed. And by greed, I mean we always make the convention that if you give a function, if you define a function by a formula, you make the domain as large as you possibly can. So I'm going to give a few examples here. So like here's a starting one, f of x equals to x squared plus 3. So my question is, are there any real numbers that we cannot square and add 3 to? We can do it to negative numbers, right? Like minus 3 squared is 9, 9 plus 1 is 10. We can do that. 0, we can square 0. 0 squared is 0. Positive number squared, that's fine, right? Search your heart. You'll find there are no strings attached to this formula, right? That means that the domain of this function is all real numbers. No strings attached. No restrictions. So that tells me that the domain of f of x here is minus infinity to infinity. Next example, f of x equals to the square root of x. How about that one? What do we need for that to be a real out? And so our default here, by the way, guys, is to study real functions of a real variable. All right, so like what is not allowed is like complex numbers, right? Imaginary numbers. In this discussion, we avoid these. We're studying real functions of a real variable by default. So here, I must make the input to the square root what? I can't let it be minus 3, right? Because that would give me square root of minus 3, which would be an imaginary number, which is not allowed here if we want a real function. So need what? We need x greater than or equal to 0 for this one, right? So what's the domain? Domain of the square root of x is 0 to infinity. So you got to watch out for the square root of a negative number. Let me throw something at you that you may or may not know. Let's see. F of x equal to the cube root of 2x plus 3. How about cube roots? We can take the cube root of what kind of real numbers? You ever think about this? There's an asymmetry between square roots and cube roots. Like you could take the cube root of minus 8. What's the cube root of minus 8? What number, when multiplied by itself 3 times, gives you back minus 8? 2. but take that 2 and slap a minus on it, right? Minus 2 times minus 2 times minus 2, right, is negative 8. That's what it takes for the cube root of minus 8 to be equal to minus 2. But the fact of the matter is, you can take the cube root of any real number. So although it looks kind of scary, the truth of the matter is that formula puts no restriction whatsoever on the input. So 2x plus 3 can be whatever it wants, which means x can be whatever it wants, the domain in this example. So no worries about negative inputs for cube root. So the domain in this case is, again, minus infinity to infinity. Right? Here, let me do a really easy one. F of x equals to 3. What's the domain of this one? When can I input x and output 3? Like what? It's just 3. There's no restriction whatsoever. I mean, it's, again, the domain is all real. So often, a lot of times, guys, the domain is just all real numbers. Like, it's not unusual for this to happen with our examples, okay? Here's one that it won't work that way. F of x equal to 1 over x minus 3. How about this one? What must we avoid? Where does arithmetic fail? I mean, you're going to give me a number, but like, what's the problem here with this formula? We could get division by what? Division by 0, right? When do we get the denominator 0 here? For what x? Division by 0 if x minus 3 is equal to 0, right? X minus 3 equals to 0 happens when x is equal to 3, right? So we need to avoid x equals to 3. What's my domain? We go minus infinity to 3, unioned with 3 to infinity. Or you could use that set difference notation we talked about, remember? You could also write this as like the set of real numbers minus the set containing 3 if you prefer. All right, let me put some dividing lines in here. So there's a bunch of homeworks you guys have where you're given a formula, and then you're asked, what's the domain of the function? So what you do is you try to figure out where does the formula fail to give you a real number output. That's all there is to it, right? So what you got to look out for? Square root of a negative number, division by 0. That's pretty much it at the moment. Now the other thing we can talk about for a function is if you're given a formula, what can you do with a formula? What can we do with a formula? One of the other important things we need to be able to do with a formula is talk about evaluation. Right, so example 10. Using formulas in example 9, let me do a few. So like f, let's do f of x equals to x squared plus 3, right? Let's try f of minus 2. What do you get? What does this mean? F of minus 2 means we plug in minus 2 in the place of x, right? So I get minus 2 squared plus 3. What's that? We get 7. Does that make sense? I hope so. For b, what would f of, so here I've got f of x equal to the square root of x, right? What is f of 9? That would be the square root of 9, which is what? 3, right? Okay. The next one I had f of x was the cube root of 2x plus 3. Let's try f of, what should I put in there to make it work out nice? What do you guys think? What cube root do you know? Well, you know, we know the cube root of 8, right? It's 2. Is there some x I can choose to make 2x plus 3 work out to 8? I guess if I do f of 2.5, things will go nicely for us, right? So f of 2.5, what's that? The cube root of 2 times 2.5 plus 3, which is what? 2 times 2.5 is 5. 5 plus 3, 8. Cube root of 8. What's the cube root of 8? 2, right? So this next one sometimes throws students for a loop, weirdly enough, because it's just so, it's such a weird idea that f of x is 3, no matter what x is, you know? So f of 3,124, 3,124, what is it? 3, right? It doesn't matter. Whatever you input, 3. And finally, the last one, I'll do a little bit different here. F of x equal 1 over x minus 3. Actually, to be honest, you guys do not usually, it's very rare for me to run into a student who has trouble numerically evaluating a function. You guys are usually fine with that. Where you'll get into trouble is when we ask you to symbolically evaluate a function. So, for example, if I was going to say f of a plus h, that probably wouldn't be, if I asked you to calculate f of, 4, everybody here would get it right, right? But what does this mean, f of a plus h? You write down the formula, right? And wherever x is, you fill in the box with whatever's here, right? So in this case, a plus h. Just like that. In contrast, if we had f of a, what would it be? Fill in the box instead of with a plus h, we just fill it in with a alone, right? So f of a would be a 1 over a minus 3 in this case. All right. So let me recap. To define a function, I can draw a line diagram like we did, right? Or I can give you a formula. That's my second way. I said there were 3 popular ways. What's the third way? Well, the third way, we're going to circle back to where we started today and talk about graph again, right? Everybody caught up with me here? I'm going to erase this stuff here because it doesn't really add to what follows. You got it? Okay. Definition. If f from a to b, all right, is a function, and we're assuming here a and b are subsets of the real numbers, all right, then the graph of f is equal to the set of pairs, x comma y, such that two conditions are met, all right? And the two conditions which must be met is, first and foremost, x must be an element of the domain. X has to be an element of A. There's like a little bit too much talking going on here. It's starting to distract me, and if it's distracting me, it's probably distracting other students too. So please don't be talking in here while I'm talking. There's enough voices in my head already. So x is an element of the domain A, and what's the other condition? Y is not just any old thing, right? Y is related to x how? Y is equal to f of x, right? So a function is uniquely related to its graph, right? In other words, just to put it in words, the graph of f of x is set of all xy such that what? Such that y is equal to f of x. This is the graph, right? To put it in less formal terms. Let's see here. So my example 11, I guess, I can draw you a picture, right? And I can actually define a function by its graph. So you can define f by graph below. And so here it is. Here's x, here's y. I'll use red. Let's suppose that that is minus 3 comma 4 goes over here, open circle, to 2 comma 2, and then closed circle like this to there, open circle, and the closed circle is 2 comma minus 1, and this final circle here is, let's say, 4 comma 0. All right? I can say these are the collection of points such that y is equal to f of x. All right? So if you're given a graph which defines a function, it's a little different than being given a formula, right? I mean, obviously. For the formula, we just have to think about where does the formula break down. For the graph, to figure out the domain, we have to think about what is the definition of graph of a function, right? It's the set of points such that the x inputs are where? They're in the domain of the function, right? So the domain, just put it in words over here. Domain of f is all possible x values seen in graph, right? And the range of f is all possible y values seen in given graph, right? So let's start out with the domain. What's the domain equal to here? Let's use interval notation. The domain of f is what? So to figure out the domain, what you want to do is like look at the x-axis and just kind of like keep track of what's going on here. So the domain starts here, right? It starts here at minus 3, right?